The process of a laminar flow becoming turbulent is known as laminar-turbulent transition. This is an extraordinarily complicated process which at present is not fully understood. However, as the result of many decades of intensive research, certain features have become gradually clear, and it is known that the process proceeds through a series of stages. Transitional flow can refer to transition in either direction, that is laminar-turbulent transitional, or turbulent-laminar transitional flow. While the process applies to any fluid flow, it is most often used in the context of boundary layers due to their ubiquity in real fluid flows, and their importance in many fluid dynamic processes. Osborne Reynolds demonstrated the transition to turbulent flow in a classic experiment in which he examined an outlet from a large water tank through a small tube. At the end of the tank there was a stopcock used to vary the water speed inside the tube. The junction of the tube with the tank was nicely rounded. A filament of colored fluid was introduced at the mouth. When the water was slow, the filament remained distinct through the entire length of the tube. When the speed was increased, the filament broke up at a given point and diffused throughout the cross-section. Reynolds identified the governing parameter, the dimensionless Reynolds number. The point at which the color diffuses throughout the tube is the transition point from laminar to turbulent. Reynolds found that the transition occurred between Re equals 2000 and 13,000, depending on the smoothness of the entry conditions. When extreme care is taken, the transition can even happen with Re as high as 40,000. On the other hand, Re equals 2000 appears to be about the lowest value obtained at a rough entrance. Improvements in apparatus for obtaining motive power from fluids, and also for raising or forcing fluids. An experimental investigation of the circumstances which determine whether the motion of water in parallel channels shall be direct or sinuous, and of the law of resistance in parallel channels, on the dynamical theory of incompressible viscous fluids, and the determination of the criterion. A boundary layer can transition to turbulence through a number of paths. Which path is realized physically depends on the initial conditions such as initial disturbance, amplitude and surface roughness. The level of understanding of each phase varies greatly, from near-complete understanding of primary mode growth to a near-complete lack of understanding of bypass mechanisms. The initial stage of the natural transition process is known as the receptivity phase, and consists of the transformation of environmental disturbances a circumflex, both acoustic and vortical, a circumflex into small perturbations within the boundary layer. The mechanisms by which these disturbances arise are varied and include free stream sound and or turbulence interacting with surface curvature, shake discontinuities and surface roughness. These initial conditions are small, often unmeasurable perturbations to the basic state flow. From here, the growth of these disturbances depends on the nature of the disturbance and the nature of the basic state. Acoustic disturbances tend to excite two-dimensional instabilities such as Laminar-turbulent waves, while vortical disturbances tend to lead to the growth of three-dimensional phenomena such as the cross-flow instability. Numerous experiments in recent decades have revealed that the extent of the amplification region, and hence the location of the transition point on the body surface, is strongly dependent not only upon the amplitude and or the spectrum of external disturbances, but also on their physical nature. Some of the disturbances easily penetrate into the boundary layer, whilst others do not. Consequently, the concept of boundary layer transition is a complex one, and still lacks a complete theoretical exposition. If the initial, environmentally generated disturbance is small enough, the next stage of the transition process is that of primary mode growth. In this stage, the initial disturbances grow in a manner described by linear stability theory. The specific instabilities that are exhibited in reality depend on the geometry of the problem and the nature and amplitude of initial disturbances. Across a range of Reynolds numbers in a given flow configuration, the most amplified modes can, and often do, vary.